Hello everyone, welcome back to our channel. Today we have a special tutorial. In this we are going to derive the complete weak form for three-dimensional elasticity problem. This demonstration video has been completely created using a Python library called Manim. It is a mathematical animation library. This library allows us to visualize complex mathematical concepts with great clarity. Using this library you can also generate voiceover for the video using computer generated voice. In this video tutorial, I have used a Google text-to-speech service, which is a free service for generating voiceover. In this video tutorial, we are going to demonstrate all these features through this weak form derivation example. Before we dive deep into today's tutorial, I have a small request. We put a lot of effort for creating this informative and engaging tutorials for you. If you like our content, please consider subscribing to our channel. Your subscription means a lot to us and it really helps to support our work. Let's dive into today's tutorial.
In this video we are going to derive the weak form for a three-dimensional elasticity problem from the given strong form equations. A strong form essentially represents a set of mathematical equations and boundary conditions that the exact solution O must satisfy at any point inside the body under consideration. The weak form, also known as the variational form, represents the problem by defining the conditions that the approximate solution must satisfy over the entire domain, typically in terms of integral equations. In the context of finite element analysis, the strong and weak forms of a problem are indeed equivalent. However, they represent the problem in different ways. Strong form emphasizes the satisfaction of equations at every point in the domain, while the weak form focuses on integral satisfaction over the domain. Despite these differences, under certain conditions, the strong and weak forms can be shown to be mathematically equivalent, meaning that they lead to the same solution. This equivalence has been demonstrated in many finite element analysis literature. These strong form differential equations are taking up a lot of space. Let's rewrite them in short form. Let's assume a symbol, nabla, sometimes also called as del operator, that equals to the column vector of partial derivatives with respect to x, y and z. If we rewrite the strong form equations in short notation, they looks like this. Let's denote these three equations as equations 1, 2 and 3. Let's work on the first equation. Let's multiply the equation on both sides by a special function called weight function. This weight function can be any arbitrary function that we can come up with. The only criteria is it has to be continuous and must vanish at the essential boundary conditions. Let's integrate the equation on both sides over the domain. Upon applying Green's theorem and do integration by parts, we get the following equation. Similarly, let's apply the Green's theorem and do integration by parts on the remaining equations 2 and 3. Final equations looks like these. Let's add these three equations. In this equation, considering the symmetry of stress tensor, sigma xy and sigma yx are equal. Similarly, sigma yz and sigma zy are equal and sigma zx and sigma xz are equal. If we substitute these equalities, the above equation will change to this form. Here, in this equation, if we define partial wx by partial x as epsilon x x bar and the other terms as shown here, the equation will be further simplified as follows. Let's simplify it even further. Let's assume two column vectors epsilon bar and sigma for various x and y terms in this equation. Substitute these two vectors in the above equation. We get the simplified equation as follows. Assuming the linear elastic constitutive law, and substitute d time epsilon for sigma, we get the following equation. This equation along with the following essential boundary conditions is the final weak form.
This is the Python source code I used in generating this video tutorial. I'll go through this code in detail in our coming videos. For now, you can download this source code. So the instructions to download this source code can be found in the comment section. I have written the instructions in the first pinned comment. Feel free to download the source code and give your feedback. If you have any questions or suggestions, we recommend you to please write them in the comment section below the video. If you like our content, please hit the like button and subscribe to our channel. Happy learning. Thank you.